The host is disabled screen sharing.
Well, good morning. Uh, we're lucky enough to have a colleague of mine, uh, Kevin Styers, and he's a professional in the data science world. And I'm going to enable screen sharing. Um, I hope. Make host. But right now, Kevin, you can't share your screen yet. It tells you can't.
Nope.
If I make you a host, I don't want to change the host to Kevin, but sure I will. Yeah. All right. So we'll ping pong back and forth. Now you should be able to share your screen, Kevin, and give us a background on R, the R programming language, and data science process in general. Thank you so much for joining us, Kevin. Take it away.
Thanks. Yeah, so I am a data scientist. I'm doing a little talk today about an app I built. It's open source. So if you guys want to see more about the code, I'll have a GitHub stuff at the end. I had a trouble titling this talk, so it's called R as a full stack language. So most of you probably have never thought of R as a full stack language. So I'll be showing a little bit of the cool R features that allow it to do that. So a little bit about myself. I'm a research associate specializing in data science for the Neon project. I use raw data to help maintenance technicians proactively repair instruments and equipment. What is Neon? So Neon is the National Ecological Observatory Network. So it's a distribution of many different observatories that have focuses on collecting standardized ecological data at a continental scale. Um, it's more common in sort of the astronomy field, which I have a little bit of a background in. You'll see large networks of satellites are constructed so that way they can focus on a specific uh, um, astrological events. So NEON is the ecological version of that. So we've got 20 different field domains, and they're all collecting different aquatic data and terrestrial data. Um, so I am focused on the TIS system, which is the terrestrial instrument system. So NEON has designed towers that collect standardized meteorological data as well as eddy covariance flux data at 47 sites across America, from anywhere from Hawaii, Barrow, Alaska, and even in Puerto Rico. We have a few sites there.
And eddy covariance flux data would be for the layman.
So eddy covariance is a calculation of um, the net breadth of the ecosystem. So we measure CO2 and H2O along a profile along a tower, and we measure how much CO2 is leaving the ecosystem and how much is coming in.
Hmm.
And that allows us to measure the quote unquote breadth of the ecosystem. So we see, is more CO2 coming into this system or is more CO2 leaving the system? So it's a way to measure the health of the ecosystem we're studying.
Hmm. Okay.
We're actually paired up with a couple other observatories that are doing this, namely Ameriflux. So just to give you guys a little bit more of an idea of what I'm talking about here, this is a TIS site at an agricultural site. So we've got measurement level booms projecting outside of the tower, capturing data. Uh, if you guys can see my mouse, there's a fan stack here. So air is pulled up through this fan, and then there's 3 PRTs in here that measure the resistance, and we convert that into temperature. We have a couple radiation sensors here. Here is a gas analyzer and a 3D wind anemometer. You see there's quite a few other sensors here that I won't get into, but there's a lot of radiation, precipitation, humidity. This measures aerosols in the air, in the atmosphere. There's a 2D wind out here. We have a soil array continuing out. You can sort of see some of these are buried in the agriculture here. But we have sites like this all across the United States. So this is another site that I used to work at. up in Niwot Ridge in Colorado. Um, so we keep on going. Here's another picture from Rocky Mountain. So this is that turbulent exchange system. So this is part of the eddy covariance measurement. So this is the top of the ecosystem that we're measuring. This is our sensors that help us figure out how much CO2 is actually moving in or out of the ecosystem. Um, and then here's that Niwot Ridge site that I showed you earlier, but in its typical state, for most of the winter, it is completely snowed in, and we have to use a snowcat to get up to the top. So um, yeah, so Neon gathers all this different data, and then puts it together and bundles it into data products, and then serves those up on a website. So here's a list of some of the data products I'm going through. So we've got a data product ID, which is just code here, and then we have a data product name, so we can makes the code a little bit more human readable. And here's a short list of some of the different streams I grabbed from the API. So you have barometric pressure, temperature, 2D winds, and a host of other streams. So my plan of attack was I want to extract a lot of data from the Neon data portal, transform that data into a digestible size, and then load that data into a Shiny app. So this is a simplified view of the extract, transform, load data pipeline. The primary reason to do this is it takes a very long time to pull the Neon data. In some cases, there's thousands of months worth of data. And if you're going to set up an application where you want to visualize this data, you're going to want to download it first, do your transformations, and then save it in a file format that your app can quickly load it. So
Okay.
by
Now,
pulling off,
when you say there's thousands of months of data,
yeah, so Neon data is stored in a site month sensor format. So every sensor has a month file. And then within
okay.
that file has like you can split it out to 2-minute average data or 30-minute average data.
Oh, the snapshot of the actual snapshot of when the data um, is taken.
Right. So it'll give
The
you
granularity.
right. Yeah. I only look at the 30-minute stuff, but if you're more of an eddy flux person, sometimes you need that higher resolution data to make your calculations.
Hmm.
Okay.
Okay.
So yeah, by pulling all of it now, I can store it in the cloud to be quickly accessed later. So this is sort of what the database structure looks like. We've got DPIDs, 2D product names, um, and so all the data products are organized in the database by these DPIDs. So when I use an R package to download the data, I'll call the data I'm downloading by this DPID. Then every site has some site information, site code, a name with a little bit more granularity, so we know it's Harvard Forest, somewhere in Massachusetts. And then we have a lat long for that site. And then, so we were only looking at the 30-minute data. So each 30-minute data has some associated statistical values. So mean, minimum, maximum, and standard deviation. And then here's the time range for which those calculations were taken. So we see this is January 1st, 2018 at 0 o'clock UTC all the way to 30 minutes UTC. So that's just a sample of what the row would look like. For those unfamiliar with R, in R you can use this double colon to specify what package you're calling the function from. This is a good habit for me, just so that way it keeps it obvious what I'm doing and what package I'm using to do that. So in this case, I'm using Neon utilities and the load by product function. So my first data product ID, this is the first variable in that function. I'm calling that DP10001. And this is that 2D wind. I'm going to grab the data from Harvard. If I wanted to specify a specific start and end date, I would do that as well, but I kind of just want all the data, so I left those blank. Check that size, another variable. And this is just a, do you want me to check the size of the files we're downloading before you download them? I also don't care how much data we're pulling, so I set that to false. And then the AVG average variable here is just what averaging interval do you want? And like I said, I only really want 30-minute data. The 2-minute data is going to be 15 times larger, and I'm about at 20 gigs now, so
Mm.
any space we can save is going to be nice.
Okay, so Kevin, on that previous slide, you did not specify in the API call, you didn't specify like a time window of the data. So this is pulling every monthly file
Yep.
that on the server, like every monthly file.
Yeah, every monthly file.
Wow. Okay. Okay.
For some data products, this can take a few hours.
Yeah. Yeah. I was just thinking if you accidentally did this in your code and you know you went away to have a cup of coffee or whatever, it could wind up pulling more if if you accidentally left out a parameter
Right.
that would limit the data. Yeah, interesting. So okay, cool.
Yeah, most people, if it's your first time, you'll see it's like, okay, it's downloading 187 files. Okay, either that's something I wanted to see, or I'm not prepared for that amount of data. The next step is to transform that data. So I use a pretty common package in R called dplyr. I'm going to use this to calculate some basic stats. So we're just taking this, we'll say t is the variable I used to call the API and load the data. So we're just going to transform t. We're going to mutate the date. So we're going to make a date variable from the end date time. We're going to group by date, vertical and horizontal position. So each sensor has a vertical and horizontal position. So how far is it up on the tower? Is it out in the soil array? Is it in the hut? So we want to group by those two variables here. And then we're going to summarize, which is another dplyr function. These are all dplyr functions. We're going to take the mean of the mean value. We're going to take the mean of the, so this function is a little bit messed up actually. So it'd be daily min would be equal to min val, and so on and so forth. And then I'll be loading all this data. So I'm using Shiny, which is our package that makes it really easy to build interactive web apps. So you can host them on a page or build your standalone dashboards. So we'll just take a quick look at some of the different apps that people have built. So this is an MRI app someone's built. Pretty interesting. So if you use this app, you can click on a specific part of the brain, and it'll give you different images from different positions. So I guess if you're a doctor, you're like, okay, this brain part right here looks funny. You're like, oh yes, this weird brain part. It kind of shows you there's quite a few different ways to use Shiny.
Sure. And the data for this web app would be individual images from the MRI data.
Right, yeah.
Yeah.
All the data would be hosted somewhere inside of the application. Let's see.
Cool.
All right, so without further ado, let's check out the app I built.
Mm.
I think one of the most difficult things in coding is coming up with names. So this is just Neon Portal Aggregator. So eventually I'll come up with something a little bit more interesting. So there are free hosting options out there, but they're not as reliably fast as hosting your own server. And it's not that hard actually. So I was actually able to launch an AWS session, kick up all the different dependencies without too much trouble. And there's lots of guides out there. It's a little bit too in depth for this presentation, but just know that it's not too bad. So this is hosted on an AWS T2 large, so it's pretty standard computer size. So if we click this link, it'll take us on over.
Is that within the free tier of your AWS account, you think?
This is $60 a month.
60. Okay.
Yeah, so I'm only gonna have this instance up running for a few more weeks as I'm just getting a lot of testing done, and then I'm gonna revert it back down to a smaller size.
Yeah.
But yeah, so we're in. So this is what the web application looks like. We can select data products up here, what sites, like I said, there's 47 different sites. We can choose one of the different statistical variables. And then this final option here is you choose date labels. So depending on how much data you select, you may want to see the month, or if your date range is pretty tight. So if we just change the date range here to just 1 year, or sorry, 1 year, we would want to see, okay, interesting, that's not working.
Well, your date
um,
labels, there was a year option in your date label there. Is it year? Is it?
there we go. Yeah, so if we want to look at the 2D wind speed, we'll have, all this is interactive, just shiny stuff. So I've just got a conditional panel that's waiting to see these things change. So as these things change, it'll pop up a different view of the sensor.
Ah, okay.
And then plot some pre-filtered data, pre-aggregated data.
S-
Um,
So yeah, temperature you would think follows an annual seasonal cycle like that. But I was looking at wind speed, trying to correlate that with something else. Looked
yeah,
pretty
wind
interesting.
speed. If we take a look up at Niwot Ridge, you'll see a very similar pattern to that diannual pattern. Whereas in the winter, it's pretty windy. And then in the summer, we're now
Uh,
August, September, August, it starts to calm down.
hmm,
And then back in winter, it's full on wind. Um, we look at the daily max to see what the maximums are. So up at this site, 34 meters per second, which for people right familiar with English units, that's almost 100 miles an hour.
mm,
And this is at the third measurement level, so this is not even at the top of the tower yet.
mm.
So it gets pretty windy up at this site. As you see, when I change the site selection, it actually zoomed in, so we see a topographic map of the site. So it's located on this ridgeline right here. So you can see there's a lot of chance for wind to come across and whip across this ridge here. Um, we can also look at other sensors, just relative humidity. We can see what the humidity looked like,
Mm.
what the maximum was for that day. Um, if you're interested in single air temperature, we can see, the it's warmer in the summer than it is in the winter, obviously.
There you go.
If we take a look at Barrow, so we're now in Barrow, Alaska, so pretty far north. We see it gets pretty cold out here, negative 33 Celsius, negative 35,
Mm.
negative almost 40. Um, so we know that's where our Barrow site is. We've got a couple other sites. So I kind of like this map feature because you can kind of see like, oh, these two sites are pretty close together. So let's see what Tool looks like. We pull up Tool, and we see it's very similar to Barrow. Yeah, so that's pretty much that's the app.
So, Kevin, earlier in your presentation, you showed us all the different sensors collecting different reading different types of data and presenting it. How are the towers connected? Is this data stored up and pulled manually because they're so remote, or are these? Is there a satellite link? How is the data transported to somewhere where you can use it from the tower?
Yeah, so all of our towers have we call it an instrument hut, or just call it a hut. In that hut, we have all the data, all the different data cables coming into a single server room. That server then batches up the data, and then will daily send it off to headquarters. So we have headquarters here in Boulder, Colorado. So all of these sites will be sending their data um, batched um, in a raw form to our headquarters database. And then our headquarters database takes that raw data and starts doing the processing of the code. I'm not on the that processing team, so I don't quite understand how all those different intricacies work. But
Mm.
all I know is that all this data is getting shipped over the internet to HQ.
Okay, I'm just curious if it's a like a microwave link, or if there's fiber out to all of your towers, or a
Yeah,
satellite
so
uplink, or
it's highly variable. So at Niwot, we do have a that mountain site that we saw earlier that actually does have a fiber link that goes up the mountain. Um, that's there's a university's building here, and we have a wire that goes all the way up to the top of the
wow.
mountain. um, some sites like out here in the sticks out in Oregon and Washington, these two sites are actually on on a cell phone tower reading. So
Yeah,
it's actually a pretty significant lag in the response time. But we do what we can to get as much internet as is feasible, and we have to work with high site hosts on what we're allowed to install. So sometimes telephone is all we can get out at sites,
yeah.
depending on how remote they are.
Yeah, that's just one of the challenges we discuss in, especially when you start talking about big data, massive streams, and this, you could combine this with video streams. It gets to be a lot of data to try and move from, the middle of nowhere out to the backbone where you can actually use it.
Yeah, that was definitely a challenge that we had. Yeah, and this was all built, top to bottom in R. R is based in C++, so depending on what functions you use, it can be actually pretty fast. So um, hopefully this kind of surprised a few people about R's capability. So I did, the front end that we're seeing now, and then all that back end with the API queries also in R. So
Interesting. So the visualization itself is a Shiny app. That's a tool you can use to make a web-based presentation of an R product.
yeah, right.
I got that right?
I can hop in the code here a little bit. This is what the user interface looks like. So um, we've got a shiny UI. Says let's build a page with the skin. We will give a title in the header. Um, we'll skip some of this, and then we can give options. So there's a select input. So this is what we're seeing up at the top. So it's a 2D wind speed and direction. So when we select that in the app, where'd it go? It's hiding underneath the
It's
zoom.
one of these.
So when we select that 2D wind speed, it's just telling my software to actually pull this data, and that changes what file I'm actually loading. Um, so there's a lot of different variables we can control. So this controls the data product variable for my data pull, and then we have a site selection. So I've got a list here that pre-populates the sites that are available. And then this is a selected site, so I just grab the second unit in that array. Then we have the statistics, and these are all just building that graph in that file. Here are the different images. So when the data product ID equals uh, the first one, give me that 2D wind sensor image. Um, oops, I clicked the wrong button there. Uh, we gotta move this
There we
to
go.
safety.
Hey, I
Now it's
think
safe.
everybody has learned in this COVID-19 thing. Everybody, we're all working online and using these real-time video teleconferencing tools. A lot of us for the first time, or some folks for the first time. And people's cats are walking across desks, and you're clicking the wrong button in the or you'll have a tab open that you didn't really want to be sharing with your boss. All kinds of good stuff happens in 2020. So I think
Yeah, sorry
we
about
all
that.
understand.
This is my first. I'm more used to WebEx and Skype, so that'll be my excuse.
There you go. And that's the other thing. You've got another one I'm having to deal with is Blackboard Collaborate Ultra. That's the one under um, our university uses Blackboard, and Collaborate Ultra is the Zoom of that environment.
Oh,
So the
interesting.
buttons are different and the options are different. There's some things you can and can't do. You can share computer audio. Like if I played a YouTube video with for you, you could hear the YouTube video, but with Collaborate Ultra, you can't do that. So,
Oh wow.
yeah, there's all kinds of different. It's just like R versus Python versus, I don't know, maybe they did this in Fortran 30 years ago. There's different tools with different options, and it's great to have choices.
Yeah, definitely. I do enjoy art. I mean, the simplicity is something I really enjoy. So, like, just to generate a plot, all I have to do is, in this UI, just say plotly output this plot object that I created in the server, and then boom, we've got a plot. Um, so all I did is create a reactive data frame here. I read in all the different some site metadata. So this is how I construct the map, I should say. Um, and so I'm just giving it, please, add all these different field site lat and longs and give me the labels for their site IDs. Um, and then set the view on the site that's actually selected. So this actually filters just to the site that has a selected and then gives me just their, and I just want the first latitude, longitude. And so that'll change the zoom as I select different sites. When I change here, I go to Woodward, this will start to re-render because it's reactive and it's
Mhm.
checking to see what values are changing. So we can actually see it's already, pre-populating and looking. And it's just the same thing on this side. There's a little bit more code here, so I was reading this file um, based upon the data product input ID, and then the stream, which would be the site ID. So it's reading that fast file, um, and then we're just plotting it down here. And there's a couple of if statements here. If we, I'll give a different plot if you're asking for the mean, if you're asking for the min, if you're asking for the max, and then we output that plot object. So these are all if statements wrapped in a reactive. So every time something changes, either the stat changes, the data product ID changes, or the stream ID changes, I want regenerate this plot. And so we store that object as P, and then we just output that plot right there. And it's as simple as that. So this was, it's 183 lines, and then the UI is another 190, and we've got an application up and running. So that's pretty cool.
Mhm.
Um, ours is a little bit simple. You can't do as advanced things, but I find as a data scientist in my realm, this is essentially all I really need. Um, so
So, even though you're not creating, classes and objects in R necessarily,
mhm.
it's you still have to know object-oriented programming in order to understand using the language. It looks like.
um, I don't really have much schooling, so I don't really know if I understand object-oriented learning, to be honest.
Well,
um,
you're utilizing object-oriented technology because you know that you're calling methods within certain um, functions in the code. So that's
cool.
interesting. Yeah, well, it's you can't get away from it. I guess was my only
Yeah.
point I wanted to make to aspiring programmers is um, object-oriented programming, object-oriented technology is everywhere.
Yeah, I definitely, as far as I know, I like to focus. I do functional programming as much as I can. So when I was downloading all the data, I made this like really big function here that would, grab all the different data. So here's that Neon utilities package, um, and then I have a couple controls in here that essentially are looking for different variables. So every data product has different variable names. Um, and so I can actually go through a list of these data products. So you see, I've got quite a few lists here, but and then for all those items and all these data products, just download those files.
Yeah.
And so I found, functional programming has definitely been something I've been getting more and more used to and more interested in. Um,
Well, yeah, there's a whole, if you were a software developer, that's what I've had some, statisticians, other scientists, remark that, that scientists are the worst coders
oh yeah.
because they just make it work, and sometimes it's not the most elegant approach. If you didn't learn algorithms and computational complexity and all of those computer
hmm
science kind of things, yeah, you can write some pretty spaghetti code, but it works. So it's interesting seeing, yeah, I mean, your approach is absolutely, from the scientist angle. I don't see anything in your code that jumps out at me as being weird, but I'm sure maybe some purist might.
Yeah, I've definitely heard the word kludge thrown around.
Kludge, yeah, that's the clue. I've written kludges because you can't get it to. I mean, you can't get it to work the way you want it to. So, yeah.
Yeah, so
So,
when I was first starting programming, that was the essence of most of my code was just, hey, it works, and that's all that really matters. And so as I've increased and developed, I've only been, I would say, seriously programming for about a year and a half. So
mm,
as I've like gotten over that first threshold of coding, I was like, okay, now I'm a little bit more comfortable with it, learning how to actually do functions, for loops, getting back into the basics. So sometimes it's like I would say it's admissible to do some pretty crappy code, so long as like you are willing to eventually go back and make it into something that's useful and reliable and dependent. So um, that's definitely a learning process that I've found.
so you come to R and data science from an environmental science educational background, correct? And you're self-taught.
Right, yeah. So I've taken one stats class. I'll be honest, I didn't really pay much attention in it. um, I've had zero programming experience at all. Most of my experience was in field biology and botany, and ecosystem services and that type of thing. My concentration was actually in conservation. So this is definitely a path that I would say not many people in my field take. But if you are in environmental science, um, being someone who can code will definitely set you apart and make it a lot easier getting into and involved with these things. Pretty much everyone can use a data scientist or a programmer on their team, especially if you're in an environment where none of the scientists are very good coders, or it's not as often as seen as a required skill. But now, as we're entering an age where there's data associated with almost anything that you're going to work with,
Mm.
being able to work with that data will set you apart, and it'll definitely give you more opportunities than being the person who can identify a salamander, I'd say.
Yeah, sure. That's I think an interesting, a valuable combination I see is if you've got domain expertise, and that can be in, logistics, manufacturing, it could be in
Oh
healthcare.
yeah.
If you know the business jargon, and then you layer on coding, whether that's in R or Python or Java, whatever it is, that makes for a really powerful combination, because then why you're doing what you're doing, and then you also can develop the solution yourself, or at least talk to developers in a way that they can understand, and you sort of understand the constraints they're working under.
Right. Yeah.
We see that a lot. Um, uh, yeah, folks are really successful when they bring both sides of that equation. So,
Yeah, I was pretty lucky. That's sort of how I started. When I first started doing this ecology stuff, I was out there collecting the plant samples, uh, and doing all the manual labor that's involved with collecting the data. And then I went from that more of the flora and observational stuff to the IS world. So I started working on the towers and stuff.
mm,
And then that really helped me transition into the science team, the data science team, because I saw firsthand what was going on in the field, and I could use that insight to help find issues that are happening across the observatory, and really using those experiences that I had as a ground level technician I found like that was really invaluable because you understand the system better than most of the other scientists on the team. A lot of people know the science code and the science of the eddy covariance and that kind of stuff a lot better than I do. But since I've seen how the field works and seen what issues arise, it's easier for me to identify like potentially huge gaps or
Hmm,
potential issues. So yeah, I definitely agree with that.
interesting. And you downloaded this data not through an operating system file download like normal. You pulled it through an application programming interface, an API,
Hmm.
in the R programming language. So some APIs, there's a fee to use. Some APIs, you've got to have some sort of credential or you won't be able to authenticate and do anything. Is this wide open? Is there a fee for pulling Neon's data? How does that side of things work?
Yeah, so Neon's data is funded by the NSF. So all of this data is available for free,
Mm.
100% free. Um, we can take a quick exploration here. There's I think 183 different data products, or sorry, 181 data products from 81 sites. So we've got let's take a look here at, let's see, let's do barometric pressure. So we can click on this data product. It gives a quick little description of what that data product is, so 1 and 30-minute averages from a zero point 0.1 hertz sensor. Um, so this is the graphical interface for the API. So if you wanted to just do API calls, you can. But if you're more of a simplistic user, you can use this UI to download the data. So
Ah,
this is all
okay.
the different data that's available.
Mm.
If you wanted to download it, it's right here. I think there's like a couple licenses. Just basically like if you do use the data, you have to acknowledge like where you got it from and like what date it was.
Oh,
Um,
sure. Yeah, yeah. You
if
definitely
you
want to
want,
cite your source.
what kind of documentation. If you only want the data, you can only get that. Um, then you're agreeing to the data policy,
Mm.
and then boom, you're ready to download this one site for 7 years. I'm not going to download it because it's going to be quite a bit of data. So it's 200 megabytes zipped. Um, so when you unzip it, it's going to be pretty sizable. But the API call, it's pretty easy. So if I can actually do some Neon utilities.
Yeah,
Gonna
that's
load
an
my product.
interesting approach because you downloaded it once you're in the R code, and that way, if it can, I would assume that when you execute that R code, it's it's going to work every time, as opposed to if you downloaded the file, you might have to change your program to deal with a new file name and that sort of thing.
Right. Yeah, it's definitely better to do it programmatically if you plan on repeating that process over and over again.
Yeah,
That's coming from someone who's done it manually.
yeah.
I was working in Excel not too long ago.
Ah, there you go. Well, there's a lot of utility in Excel still.
Definitely.
Okay, so the National Science Foundation funds Neon's efforts and makes the data available. Is there just curious if there's a like an international um, effort, where you could pull similar data sets from stations outside of your network?
Yeah, so there is some effort on actually getting the data, more integrated with other systems. I'd say we're still in the early stages of doing that. Um, it's pretty easy to get our system, like it was actually really difficult. Sorry, it's difficult to get our numbers and our data out there in the standardized processes, and then integrating that data with other networks isn't always super easy. The one notable partnership that we do have is with Ameriflux.
Hmm.
Um, and so we send our data out to them. And this is probably one of the biggest flux eddy covariance networks. Like, I'm not really familiar with this. Actually, a different website. One sec. There we go. Ameriflux. Here we go. So you see, there's all these different sites, and so we do
Ah,
contribute to um, 47 of these sites on this list. So um, this is probably our biggest collaboration. The edicovariance data is probably our most valuable data by far. It's most expensive to collect, and then B, it's used in some pretty interesting climate change models. I'm not a modeling scientist by any means, but I know that scientists are out there using all these different sites to grab and analyze eddy covariance across geographic scales.
There you go. Yeah, and beg your pardon. That's assembling data, especially in the whole big data analysis, is assembling data from different sources and doing, like you said, the ETL or data cleansing, wrangling. Sometimes the other term you'll hear,
Yeah.
just and then you used a term that I'm just now learning, data monging.
Yeah.
Talk about data monging here for a second.
Oh, um,
What is it? Why do you
let
need to
me
do it?
data munging. Let's see.
Munging,
We see exactly what we're talking about.
data
Yeah. So
munging.
it's yeah, wrangling data is
Yeah,
I think they're all referring to essentially the same thing, which is probably what a lot of us find is the most tedious part of data analysis. Is in most cases your data isn't formatted in a beautiful, easy to use, already so like someone with a degree assembled the database and made it all pretty. So in some cases when you're pulling that data, you've got to do quite a bit of um, manipulation and editing to ensure that the data is like what you want, what you're expecting. Um, so when I was working with the Neon data, since it's already prepackaged in those data products, it's already super easy to do analysis on it because you can reliably expect the data to come in as a specific way. Um, there still is a little bit of data wrangling. I think I assign, I want to, I make it some of these have to be converted into dates or factors. But beyond that, like there isn't much data munging actually going on here. For making, I do take those big files and then save them into smaller aggregations. So this is the aggregation function we were looking at earlier with
sure.
the correct min, max, mean sums. Um, and so there's that's all I did. So this was
Sure.
just to reduce the file size to make the load faster. Um, but yeah, so it really wasn't much wrangling. Usually there's like reshaping where you have to go from wide to long and then rejoining and uniting and a lot of crazy stuff that can happen. But at least for this project is relatively simple.
Well, that would make sense if you're pulling data from an API from a single source. You would, I would think you would have less wrangling and transformation that you'd have to do. But if you were pulling this stuff from different historical databases
Right.
collected in different formats and all, oh yeah, you'd have all kinds of trouble,
Yeah, and
gaps
you
and dupes and format
mm,
weirdness.
yeah, it does get a little tricky when you are combining data that was collected in separate ways with separate means and separate techniques. So um, one of the analysis I've done was we have a software that controls the tower and tells, which measurement levels to start sampling air and which measurements, it kind of controls the whole system.
Mhm.
And so we have one database that says that system is up and running or not up and running. Um, and that it's just a single moment in time. Every hour it'll ping and say, hey, are you on or off? And then it logs that data in the database. So in between, so if you have two off periods, you don't know if in the middle it had been turned on or not. So you have to make some assumptions with your data. Um, so that way when you do an analysis, you have to let your stakeholders know, like, hey, I'm pretty sure that when the CNC stuff is off, um, none of these processes are running. And then here's my analysis. And there's this caveat that I'm relying on not so frequent data to assume if it's on or off. Um, so yeah, sometimes you have to be a little bit careful about how and where you pull the data, and when you're merging two data sets together to make an analysis, you got to make sure that your data is actually going to give you a valid result. So that's something to be careful about.
Okay. So, hey, one other topic, and I know I'm hitting you here somewhat sporadically. Another topic that folks that are new to R might like to know about is the tidyverse. That's a play on words for universe and tidy.
Yeah.
So, what is the R tidyverse?
Yeah, so there's pretty much two factions in the art world that I've come to know. There's people who who like to use just the base R functions, um, which I'm not in that faction, so I can't really tell you how to use base R. um, I'm in the tidyverse sort of universe, mostly because transitioning from Excel to R using the tidyverse made it really easy. Um, most of the functions do exactly what they say, and they're pretty self-explanatory. So we're looking here at this dplyr function, rename at. Uh, we can take a guess at what the 7 means. It's the index of the column. So at column number 7, please change that to be mean. And then at 8, change it to min, and so forth. So
Hmm.
you can see how it's pretty easy to understand. I think in base it would be some crazy, double. What I always call base is like the real coding because I don't understand. It looks very fancy and I have no idea what's going on. So that's a little bit of example and then here's a mutate function. So it's saying this new variable date, make it equal to this variable here. So this is date now equals end date time as date.
And
Um,
the base is the base language,
right, yeah.
the R library. Okay.
Yeah, so this is our library. So there's some like very simple base stuff that is pretty I say ubiquitous.
Mm.
But you can do mutates and group bys and summarize in base. But depending on what exactly you're doing, it could be very, very slow. Let's see. I do have an R document here that I made a while ago, kind of comparing the speeds of different things. So um, if we look at the speed of a filter, we have the dplyr universe here at 1.5 times the fastest. So it's about 60 to 7% slower. The base is actually pretty quick. It's pretty close to data table, which is one of the faster packages out there. Um, but if you're doing, let's say, a join in base, so let's see, the base join is merge data product 1 and data product 2. This can take, let's see, it took 261 seconds to actually join those two data frames. Whereas if you used dplyr, it only takes about 4 seconds. So
Yeah.
um, in most cases, you'll find that these dplyr packages and data table and tidy table, all these other packages are going to be better than base. But in a lot of instances, there's really no winner. So if we do a filter, you can see that these are all within pretty much a standard deviation of each other. So
Mm.
the elapsed time goes from 0.22 seconds to 0.26 seconds. So it's really who cares what you use.
Mm.
And this is with a million row data set, so it's not too large. So ultimately, I kind of just lean to using dplyr, which is a tidyverse package, as it's simple and easy to read. Like I said, like when we're doing the summarize call, and
Mm.
we're making these means, it's pretty simple and easy to see what's going on in the code. Uh, it's definitely I would feel I started trying to learn Python at first, but once I started using R and the tidyverse stuff, it was just so easy and simple for me to understand that it made learning R like really really easy. Um,
Well, sure, whichever one you're more comfortable with. I know there are camps Some folks are R versus Python. I think a similar approach is when you can like import the pandas library or
Yeah.
matplotlib or yeah, there's amazing functionality out there for R and Python and pretty much every language now that's open source. It's just incredible what you can get done with a line of code compared to, I mean, if you can imagine having to write this from base
Oh,
Fortran or Basic or whatever, it was just be ridiculous.
yeah. A line that I often repeat is, I'm standing on the shoulders of giants here, because
Yeah,
um, to actually code this mutate function, I don't know if I have the background knowledge and coding background to actually code that up, but because someone out there contributed to this free software and made these robust and easy to use packages, it's really allowed me to take my coding to the next step. So yeah, I applaud those people out there in the free software development. I mean, I paid nothing to launch this app besides AWS server fees, but all this code, all that stuff, nothing's proprietary. It was all free, and just to have the power that we have in today, that we can make apps for free.
sure. And
My
and the data's free. That's the other thing. There's
Yeah,
so much public domain data flowing in out there, and even commercial companies are giving away free data just to get you linked in, connected to Google or Amazon or Facebook, whatever the case may be.
yeah.
So, all right. Well, we're coming up on the end of our session time here, Kev. Have you got any points that you wanted to make about learning R or your domain expertise in general?
Yeah. I guess I would say, if you are interested in R, there's a lot of resource out there. For me, not affiliated, but I use DataCamp. Um, I probably redid that initial tutorial on how to actually assign variables and all that basic stuff probably 65 times. Um, and then slowly built up my skills and went to the other modules in DataCamp. But pretty much any software you use, it's up to you. For me, as a data scientist who's not really interested in building complex UIs or really crazy APIs or anything like that, um, R was all is just enough and all I really needed. But if you're already in Python, that's awesome, because that was the language I had the most struggle actually learning, and even though it's probably one of the easier ones to learn, but Python is also going to serve the same purpose and will be around just as long. So uh, yeah, whatever language you're coding in, it's cool. I'm pretty agnostic about the whole language wars or anything like that. Some people say R will be gone in a few years. I doubt it, but uh, feel free to, if maybe this will inspire you to check out R. You probably didn't know about all these different applications like Shiny. It feels pretty undervalued or not really open or understood. So you
Yeah,
see how
it's way
quickly I
cool.
made a web app with interactive maps and graphs, and it's pretty simple. I'm not a web developer by any means, so I guess I am now. But
Yeah, the tools are fantastic. All right. Okay, well, Kevin, thanks. This was highly informative to somebody that's new to R, but then even within your environmental data functional area, it was great having an insight into that world. So go ahead and click off record, and we'll end this session and put it in the books. I
cool.
hope it goes to my machine.
Here we
So
go. Let's see. Stop there.
still says recording.
Here, let me see if I can pass you the
Yeah,
host.
please. I am now the host. I'm going to stop recording. All right. Thanks again, Kevin Styers.